Assalamualaikum guys. So today I'll show you how to construct Bode plot. Okay, previously I have shown you that the system, the transfer function can be analyzed by using root locus and also Bode plot. So if by using root locus we can see that whatever the value of gain that gives you the locus at the right side of the imaginary line, so the system is still stable. But if the gain k gives you the locus at the right side of this imaginary line, so the system is not stable. Whereas for the Bode plot, we know that we will have gain margin and also phase margin, right? So as long as the gain margin is at the right side of the phase margin, so the system is stable. Okay, when we increase the value of k gain, so we actually move this gain line upward. Okay, so this phase margin will move to the right, okay, until one time it will be at the right side of this gain margin, so the system is not stable anymore. All right, so now we try to draw manually the Bode plot. Okay, so we have two plots that we will have to construct. One is the gain plot and one is the phase plot. Okay, right. So this is the advantage of Bode plot. So we know that by using semi-log graph, okay, we will see, since we know that frequency is in a very huge range, it can varies from 10 to the power of -1 hertz up until 10 to the power of 7 hertz. Okay, so it's very huge range. So that's why we use semi-log graph, so that we can see the difference even though we have the margin in a very low frequency as compared to a very high frequency. Okay, there are 1, 2, 3, 4 steps in drawing a Bode plot. Okay, first is to rewrite the transfer function in a proper form. Okay, so I'll show you later. Okay, and then from that proper form, we will separate the transfer function into its constituent parts. It means that we will have numbers of parts to solve within the transfer function. And then we will draw the block diagram for each part. So let's say in one transfer function we have 5, 6, 7 parts, so we'll have to draw each part. Okay, and then we draw the overall Bode diagram by adding up the resulting from the part 3 just now. And remember that this number 3 and number 4 steps will be done for both gain graph and also phase graph. Okay, let's go to our first example. First step is to rewrite the transfer function in proper form. Okay, so if we have this transfer function 30 times s plus 10 over s squared plus 3s plus 50, okay, so we have to convert this form into a proper form, as we can see here at the rightmost. If we have more complicated form, we have to factorize everything. The simplest factor form, as we can see at this example, and then we have to convert into this form. Okay, what is proper form for Bode plot? The proper form is that we have to make sure the constant number at the end of every s, it is to the value of 1. Okay, for example, for this case, we have 10 and we have also here 50. Okay, for this s plus 10, we have to divide by 10, and then we have to multiply back with 10. Okay, so this part will become s over 10 plus 1, and we have this 10 here. Okay, for the bottom side, we have s squared plus 3s plus 50. We divide all by 50, and then we multiply by 50 again. Okay, so to make sure that the equation is still balanced. Okay, so it becomes 50 times s squared over 50 plus 3 over 50s plus 1. Okay, so this 30 times 10 over 50 is 6. Okay, and this will be our proper form. So this is one example. Okay, the second part is separate the transfer function into its constituent part. Okay, the constituent parts will be any constant to be one part. Okay, poles at the origin will be another part, zeros at the origin will be another part, until number 7, complex conjugate zeros. Okay, so this is one example. Let's say you have this transfer function. So this is actually equals to, okay, we divide the top part by 10, and also we divide s plus 3 here with 3, and plus s plus 50 with 50. Okay, so we'll get 2 times all of this. Okay, so we have 1, 2, 3, 4 constituent parts. Okay, for number 3, there are rules to draw all of these constituent parts. For example, for a constant, you have to draw a line, a straight line, with the magnitude of 20 log constant just now. Okay, so that is for magnitude graph or the gain graph. Okay, for the phase, okay, if the k is more than 0, so we have to draw a straight line at the value of 0 degrees. Okay, if k is less than 0, so we will have to draw positive minus 180 degrees. Okay, so these are all the rules. Okay, for real poles, for real zeros, for poles at origin, for zeros at origin, for under damped poles. So this one is s squared. Okay, and also under damped zeros. Okay, so this one is at the top, poles is at the bottom of the transfer function. So these are all the rules. Without further elaboration, we go straight to the example later. Okay, how you want to draw the Bode plot. Okay, so if we have this kind of parts, so this is how you draw it. Same goes to all of this. Okay, we go to the example first, and then you go back to this part to understand what is actually happened. Okay, right. So this is one example. Okay, the following example illustrates this procedure. So let's say we have g, the transfer function. Okay, so the first step is to rewrite the transfer function in proper form, and then we separate the transfer function into its constituent parts. So this is how you rewrite in proper form. Okay, we know that this 20s plus 200 need to be divided by 200. So it becomes s over 10 plus 1. And this 1000 times 200 becomes 200,000. Okay, for the bottom side, this 2s over 2 divided by 2. And for this part, we have to first extend it to s squared plus 100s plus 10,000. So from here, we divide with 10,000. So this one we divide by 2, this one we divide by 10,000. So we have total 20,000. So from this equation, we will have, after we divide the top part with the bottom part, we will have this equation. Okay, 100,000 s times s over 10 plus 1 over these values. Okay, and then we divide it with 10,000, so we will get this value. So this is the final equation in a proper form. Okay, we assign color for all these parts. We have 1 part, 2, 3, 4, 5, including this 10. Okay, so 10 is the constant just now. Okay, so this is how we look at semi-log graph. Okay, so we can see that the only linearly distributed point is every decade. Okay, we call decade from 0.01 until 0.1 is one decade, from here to here. From 0.1 to 1 is another decade. Okay, 1 to 10 is one decade. 10 to 100 is another decade. Okay, and so on and so forth. Right? We can see also for the y-axis, this is the first graph. Okay, the magnitude graph, the gain graph. So the magnitude is in decibel, dB. So the value is, usually we will have 0, 10, 20, 30, 40, or we can have 0, 20, 40, 60, and up. So this is how we draw the axis for semi-log graph. Okay, and please make sure that it goes like this. It means that the grid for x-axis is big, small, 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 small. We have 10 of it. Okay, 0 0.01, 0 0.02, 0 0.03, 0 0.04, 0 0.05, 0 0.06, 7, 8, 9, 0 0.10, 0 0.2, 0 0.3, 0 0.4, 0 0.91, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 20, 30, 40, 90, 100, 200, 300, 400, 900, 1000. Right? It goes like that. And please remember that it always from big grid to small grid. Okay, so if you have your graph sheet of semi-log graph, okay, make sure that you do not hold it in the wrong direction. Okay, so make sure it's big to small, big to small, big to small, like this. All right. Okay, so how to draw? We go for the first one. Okay, we can see that the S is the top side, and then we have also S over 10 is at top side, and 10 is at the top side, the numerator. Okay, the denominator just now we have S over 1, and also we have this one, S over 100 squared. Okay, so whatever is at the numerator, so the line will go either straight or upward. For those S's at the bottom side, the denominator, it will go either straight or downward. Okay, right, so we go for the red one first. Okay, so it shows here S over 1. So where is 1? 1 is here. Okay, so for S over 1, without S plus anything, is plus S plus 0. Okay, so you will have this line. Okay, a straight line upward, because the S is at the numerator, upward, straight from the beginning until the end. Okay, it will pass 0 decibel, see, the 0 decibel at the value of 1. So this one is from here. So it means that if you have F over 10, for example, so you will have the same line, the same slope, okay, but it will be here, intersect at 0 magnitude and the frequency of 10. So it will be here. Okay, if it is S over 100, so it will be here. If it is S over 50, so where is 50? So here is 10, 20, 30, 40, 50. So it will intersect this point where the magnitude is 0 decibel, okay, and the frequency is 50 radians per second. Okay, so what is actually the slope? If the S is at the numerator, at the top side, so the slope is positive, it goes upward. Okay, and the slope for S is 20 decibel per decade. Okay, this is decibel, this is 1 decade. Okay, so here it's from this point up 20 decibel in 1 decade. Okay, 20 decibel, 1 decade. So this is the graph. So if it starts from 50 just now here, okay, if it starts from here 50, so we know that 1 decade is 500. Okay, so from here, from 50 to 500 and 20 decibel. So 20 decibel per decade. It is always 20 decibel per decade. If the S value is at the bottom side, at the denominator, so it will be negative slope. So it will be negative 20 decibel per decade. Okay, but the line is similar like this one, straight line only. So we go to the next point is the blue line. Okay, we know that this part is at the denominator. So we know that the slope will be negative. It will go downward. Okay, but instead of it is only one line like this red line, it will start from 0. Okay, and look at this value 1. Okay, so go straight from 0. When you reach 1, it goes down, and the slope is the same since this one is also s to the power of 1. Okay, so 20 negative 20 decibel per decade. Okay, so from 1 to 10. Okay, we look at the third line, which is this magenta line. So it is in numerator. So we know that the slope is upward, and it is only s to the power of 1. So it's 20 decibel per decade. Same slope with this one. Where it starts going upward is from 10. So it starts from 0. When it reaches 10, it goes up until the end. Okay, this one also, it goes up until the end. Okay, for this case, s is to the power of 2. Okay, so when it is s to the power of 2, instead of 20 decibel per decade, it is 40 decibel per decade. Okay, where it starts here 100. Okay, so this is orange color. Okay, it starts from 0. When it reach 100, it goes down. But see, the slope is not only 20 decibel per decade, but it is negative 40 decibel per decade. And remember, we have another constant here. We have constant of 10. Okay, if you look back at our rule just now, for a constant, we need to have a line, a straight line of 20 log k. So since our k is 10, so log 10 is equals to 1. So 1 times 20 equals to 20 decibel. Okay, so we go back to our graph just now. So see, so this gray color line is a straight line at the value of 20 decibel. Right. So these are 1, 2, 3, 4, 5 lines from these 5 parts, constituent parts. Okay, so the next step is to add up all the values of all these lines. Okay, we start from 0.01, for example. We can see that we have all 5 lines. Okay, we have red lines here. Okay, we have blue line here, so 0. Red plus 0 plus magenta is 0 also. Orange is 0 also. Red plus 0 plus 0 plus 0. Okay, so it will follow until here because nothing changed. Okay, all lines have not changed in direction from 0.01 until 1. Okay, so we will have this line. Okay, red line, plus blue plus magenta plus orange. So we'll get this. Up to this point, okay, the blue color changes its direction from 0 degrees to this slope, negative 20 decibel per decade. Okay, so it means that the black color will reduce by 20 decibel per decade. Okay, so this one is 20 decibel per decade minus 20 decibel per decade. You will have this line up to this point. Okay, when it reaches this point, we can see that the magenta line is changing its direction. Okay, from straight line to upward 20 decibel per decade. Okay, we know that the total is 0 degrees. Now it goes up 20 decibel per decade. Okay, so it goes up 20 decibel per decade. Okay, this point is goes straight up. This also goes straight up. But until this point, we can see that the orange line will change the direction from straight to downward of negative 40 decibel per decade. For this line is 20 decibel per decade. So 20 decibel per decade minus 40 decibel per decade, it becomes negative 20 decibel per decade. So you will have a downward slope, same with this one, negative 20 decibel per decade. So you will have this line. After this point, there is no change of direction anymore. Okay, for any of these 5 lines. Okay, what next? Remember, we have this constant just now that we haven't add up to the total value. Okay, so this is your line. Okay, and then if we add with another 20 decibel, we are actually lifting this black line upward. Okay, from this line upward 20 decibel. So this is your final gain line, we call it. Okay, so this is only for the first graph, which is the gain, the magnitude line. So after this, we will draw the phase line. Okay, for this, we can remember that we are looking for any intersection with 0 decibel. So this is 0 decibel line. So it intersects here and also here. And we are interested on the rightmost intersection. So this is the point that we are looking for. Okay, so this is the intersection with 0 magnitude, the 0 decibel. Next, we draw the overall Bode diagram by adding up all the result from part 3 just now. And we will have this straight black line. Okay, whereas if you draw it by using software, Matlab for example, you will get this tiny line, curved line. So that is the actual magnitude line, or we call it gain line. Okay, so this is the estimation line that we draw. Okay, right, so we go for the phase line, create the phase plot. Okay, so this is our constituent parts just now. We use the same color, okay, red, blue, magenta, orange, and also uh, gray, okay, for these 5 parts. Okay, we start with red. Okay, if it is S at the top side, okay, at the numerator, okay, S only, S over 1, okay, so we draw a straight line at 90 degrees. That's it. Okay, so if we have denominator S over 1 plus 1, okay, so where is 1? 1 is here. Okay, 1 is here. Okay, so you will have the slope of the line, this line is 90 degrees, negative 90 degrees over 2 decades. Okay, it starts 1 decade before 1 and it ends 1 decade after 1. Okay, since here is s over 1, okay, and its denominator, so the slope is negative. Okay, it starts 1 decade before, it stops 1 decade after. Okay, so it starts from 0 since s over 1. So when we reach 0.1, it goes down. The slope is negative 90 degrees per 2 decade. Okay, up to 1 decade after 1 is 10. Okay, up to 10, so we go straight back to a constant value. Okay, if we look at the third line, which is the magenta line. Okay, we can see that the slope is the same. The difference is only one is negative slope, one is positive slope, but it is 90 degrees over 2 decades. Okay, since this is s over 10, okay, it will start 1 decade before. So 1 decade before 10 is 1. So it will start from 1 and it will stop 1 decade after 10, which is 100. Okay, once it reaches 100, it goes back constant. Okay, we go to the orange one. Okay, so this one is s over 100. Okay, so since this is s squared, okay, we know that we have to twice the slope value. So instead of 90 degrees per 2 decades, it is negative 180 degrees per 2 decades. Okay, since this is 100, it starts 1 decade before, so it will start from 10, goes down, and it will stop at 1000, and it goes back constant. For constant value, we have no line for this. Okay, right? So now we have 1, 2, 3, 4 lines. Okay, we have to add up everything. Okay, we can see here we have blue, we have magenta, we have orange line, okay, with value of 0, and we have also 90 here. So the total is 90. Up to this point, we have change of direction for blue color. It goes down. So it will follow the same slope. Okay. Up to this point, we can see that the magenta changes its direction. It goes up 90 degrees over 2 decades. Okay, so as we know that this one is negative 90 degrees per 2 decade, this one is positive 90 degrees per 2 decade, so the line will become straight. Okay, when we reach here, okay, we can see that the orange changes direction. It goes down, but it's not only 90, it is negative 180 decibel per decade. Okay, so the line, since this one is 90 degrees minus 180 degrees, it becomes negative 90 degrees per 2 decade. Okay, per 2 decade. But we know that when it reached this point, okay, this magenta line changes its direction again. Okay, it changes from 90 degrees to 0. So it means that this line will go deeper, okay, from negative 90 degrees to negative 180 degrees. Okay, Up to this point, we can see that the orange line changes its direction. Okay, since we know that this line and this line is the same slope, okay, when it goes straight, this one also will go straight. So this is your final phase line. Okay, so if we look at the actual phase line, it is this black thin line. Okay, and this one the estimated line that we draw. Okay, it's not the same, but it can be represented by this estimation. Okay, right. Now, is the system stable or not? The answer is stable, because remember, for the gain line just now, we are looking for this. It's supposed to be here. Okay, we are looking for this. Okay, intersection with this 0 decibel, the rightmost. Whereas for the gain line, we are looking for any intersection with negative 180. But for this case, there is no intersection with 180. So it means that this system is always stable. Okay, this is the law for the Bode plot, where if we have intersection with 0 decibel, we go downward and we find the phase margin. Okay, so this is positive phase margin. Okay, and then we look at the intersection with negative 180. We go up and we look for this gain margin. Okay, if this is the point, so it is a positive gain margin. So this is stable system. For this case, the system is always stable because the phase line is not reaching negative 180 at all. Okay, so if we use Matlab and we write this command, okay, to have the same transfer function, and we use ISO tool, okay, so you will get this line, exactly the same line as we have drawn just now, these two line, and this one is stable. If we look at the root locus, none of the line is going to the right side of the imaginary axis, so everything is at the left side, so the system is always stable. Same goes to the step response. If you look here, okay, it goes to one value, so the system is stable. Okay, even though we have a very huge error, but the system is always stable, but stable with error. Okay, right. So you may try this one also. This one a bit simpler. Okay, so we have 100 over s plus 30. So we have 4 steps. Okay, so follow all of these steps. Okay, this is the proper form, and this is how you draw it. So you will get this line and also this line. So it intersect here with 0 decibel, and this one it never intersect 180. It goes to only negative 90 degrees of phase. So it means that this system also always stable. Okay, so that's it for today. So hopefully you can understand what is Bode plot, how to use it to check whether our system is stable or not, and try to make more exercises. Okay, and remember to draw it by using semi-log graph. Okay, if you have not seen it before, so try to find it and use it for this Bode plot construction. Okay, so all the best to you guys. See you next time. Bye bye.